Okay, so we're going to be talking about waiting times. It says here, we have seen that for repeated Bernoulli trials, we get a probability distribution of this. And this is, again, a formula that you have to know. Where P is the probability of success and Q is the probability of failure. So we only have two options, success or failure. This tells us the probability of getting X successes out of N trials. So what is the probability of rolling 3 2s if you roll a die 20 times? Joanna, can you help me out here? What would be my N for this? Good. So N equals 20. What would be my probability for success, Johnny? What is the probability of rolling a 2? Good. David, what is the probability of failure for this? Very good, 5/6. And then K is what, Noah? K is the number of successes that you want, the number of outcomes that you want. No, that's what we want. The number of times we want the 2 is 3 times. So Mitchell, can you please plug this in to the formula? What is the probability of getting 3 2s? Good. Very good. So once I plug all of that into my formula, you will get here that you have a probability of 0.2379. So you have a 23.79% chance of rolling 3 2s if you roll a die 20 times. Okay, the next logical question to ask is how many times should I have to roll the dice before a 2 comes up? This is given by something called the geometric distribution, but is better known as waiting time. The geometric distribution is the probability that you will experience X failures before finally getting success is given by, and do we have it? Is given by P times Q to the exponent X. So this is a different way of looking at the problem. I don't need it. So it says here, note there is no combination at the beginning of this distribution because there is only one way that our scenario can occur. At the end of all of the failures, again, we have that success, and we just want to know how many fails do we have before we have that one success. Also, there is no exponent on the P since there is only one success. We're stopping at the success. We want to know how long it will take to get to that first success. Geometric distributions have the same requirements as binomial, only 2 outcomes, repeated trials that are identical and independent. So it says here the expected number of failed trials before you get a success is given by Q over P. So again, these are all formulas that you will have to memorize for your test. So we have the expected value, and then we have the probability, the number of failures before you get a success. Okay, so we're going to go over some examples here. It says, what is the probability that the first 2 you roll is on the 4th roll? Okay, so when I'm doing this question here, I have the probability of when X is equal to 6. So what I have here, what is actually happening, why do I choose X? X is the number of failures for this example. So when it's saying here that the first 2 you roll is on the 4th roll, that's saying your first roll is a fail, Your second roll is a fail. Your third roll is a fail. Your fourth roll is a success. So we're only looking at the fails, which is why x is equal to 3. So when I'm doing this, I'm going to write out my formula, p times q to the exponent x, where again, x is the number of fails. So I have here the probability, p and q are still the same, that you get a 2 is 1 over 6, times the probability that you don't get a 2 is 5 over 6, raised to the exponent 3. So when I put this into my calculator, I get 0.0965. So there is a 9.65% chance that you will get your first 2 on the fourth roll. Does anyone have any questions about this? Okay. Okay, perfect. Thank you. Okay, the next one says, what is the probability of getting a 2 in the first 3 rolls? So this is different. This one actually becomes a little bit more longer because what it's saying here is that you can get your probability, you can have 0 fails, so you can get a 2 on the first roll. You can have 1 fail, which means you get a 2 on the second roll. And you have 2 fails before you finally get it on the third roll. So when I'm doing this, this is saying when I have x is equal to 0, so I'm going 1 over 6 times 5 over 6 to the exponent 0. This would be saying that I get a 2 on my first try. There are 0 failures. I roll the dice once. I get that 2. We're done. There's another case to this. Or I could get it on my second roll of the dice. If it's on the second roll of the dice, that means I had 1 fail first. So I'm going to keep rolling. So I roll, I get any other number but 2. On my second roll, I don't need it. On the second roll, I get a 2. So this would be saying this is on my second try. Plus, again here, I have, this would be getting a roll, the 2, on my third try, 5 over 6 to the exponent 2. So again, that would be saying a fail, and then my third roll, finally I get that success, which is 0.4, oops, no, I didn't mean to write that there. I meant to write this is my third try that I get the 2. And then you would get that your final answer is 0.4213, which is a 42.13% chance. Okay, so it's kind of a backwards way of looking at it from what we've done. We're always talking about the number of fails. Does anyone have any questions about this? Okay, for 1C, it says, which roll would you expect to be your first 2? So again, now we're talking, we see that word expect, which means we use our expected value formula. So I'm going to see here, your expected value is your first 2. So my formula for expected value is Q over P. Another way I can write that, bless you, is 5 over 6 divided by 1 over 6. When I'm dividing fractions here, it becomes 5 over 6 times 6 over 1. These cancel out, so you're left with 5. Now, the tricky part here is I'll let you copy that out, but I'll explain what the actual conclusion is. This number here is actually telling you the number of fails. Hello? Hi. Yes. No. Okay. Okay. Yep. Okay, bye. Um, okay, so that's the number of fails. So it's saying here we would expect 5 fails. So with 5 fails, we would expect our first 2 on the 6th roll. Does anyone have any questions about this? Okay, so let's talk about this. What is the probability that the first pair will occur on the 3rd roll? Spencer, can you help me out here? Can you tell me what my P is equal to here? Not, no, not 1 over 12. Can someone help me out? What's my probability of success here if I want the doubles? It'd be 1 over 6, or we can write 3 over 36, whichever, or not 3 over 36, 6 over 36. So how do you get that? You can get doubles, you can get ones, you can get twos, you can get threes, you can get fours, you can get fives, you can get sixes. So there's 6 ways you can get doubles out of, and then on that doubles chart, there are 36 options to get, which means the probability of failure here would be what, Scott? $30 over 36. That would be my probability of failure because there are 30 other options. And then I want to find out that what is the probability that the first pair will occur on the 3rd roll? What would be my X value here, Curtis? Very good, because that means that there's 2 failures before we hit that double on the 3rd roll. So the probability when X equals 2 is 6 over 36 times 30 over 36 to the exponent 2, which gave you what as an answer, Eric? Okay, 0.1157, which is an 11.57 or 6% chance that you will get your first double on the 3rd roll. Does anyone have any questions about how many of you were able to get that? Okay, anyone have any questions if you weren't able to get that? Okay, the next one, it says, how many times would you expect to have to roll the dice in order to get your first double? So I want to find the expected value for the first double. Pat, what did you do for this? Yep. Other way around. Okay, and then when I do this, it ends up becoming multiplication, 30 over 36 times 36 over 6. These cancel out. What do I end up getting for an answer here? Mike? Good. So, Joanna, how many times would you expect to have to roll the dice in order to get your first double? Good. This is saying 5 fails, which means you have to get 6 rolls in order to get your first double. I don't want this. I don't know. You can keep. That's for you for all of your other classes. Okay. Our last set of examples here. Example 3, what is the probability of getting a sum of 7 in fewer than 3 rolls of a pair of die? Okay, so fewer than 3 rolls means 2 rolls is what we're talking about. Okay, so fewer than 3 means 2 rolls. So what that's saying here is x is equal to 0 or x is equal to 1. Ben? You have this in your note. Okay, so are we clear with this? Fewer than, what is the probability of getting a sum of 7 in fewer than 3 rolls means it's actually saying what's the probability of getting a sum in 7 in 2 rolls. You can have fewer than, so it's 2 or less, which means you can have a fail. X could be 0, which means you get the 7 on the first roll. X could be 1, which means you don't roll a 7, then you roll a 7. So that 3 there, again, you just have to be careful of the wording there. So I have here the probability of X equals 0 or 1. What would I fill into this? Johnny, can you help me out? I want to find my probability. My first case is going to be x equals 0. What is the probability of success here, Johnny? David, can you help me out? How many ways can you roll a 7? Pardon? Oh, you can. Eric, how many ways can we roll a 7? No, we can roll a 7 more than 6 over 36. There are 6 ways to roll a 7, which means my Q would be what? Johnny? What would be my Q? So now, can you help me out? What would it be for when x equals 0? I just want it for x equals 0, but yes. Mm-hmm. Mm-hmm. Very good. And I'm going to add that with when there is 1 failure. So David, what will I write for that? Very good. Okay, put that in your calculators and we'll see what you get. Hello. Hi. Yeah, did he finish that workbook? Is he ready to write? Okay. I have 2 quizzes for him, and then I have a test. The test I'm probably aiming for this Thursday. Okay? Okay, bye. Okay, what did you get for an answer, Noah? Anyone get anything different? Yeah. So there's a 30.56% chance that you get a sum of 7 in fewer than 3 rolls. Okay, our last example here. Does anyone have any questions about that top example? The wording's a little bit tricky, so it's just something you're going to want to be aware of. It says in example 4, in a game, a person flips a coin repeatedly until they finally flip a head. When they do so, they win 2n. So $2 times the n, which is the number of flips that they made. What is the probability of the player winning $8 in a single play? So if I want to win $8 here, I can kind of do the math. How many times would you have to flip the coin in order to win $8? 4. This would be like saying 2n is equal to 8. Divide by 2, divide by 2, n equals 4. So I would have to flip the coin 4 times in order to get $8. Do you have to show that math? No, but that's how you get that math. So it's saying I would have to flip it 4 times, which means here, if I have to flip it 4 times, n equals 4, that means I have 3 fails before I have my success. Because on the 4th roll, or on the 4th flip, I get that head. Yes. They get 2 times the number of flips you get, or it took to get the head. So when I want to figure out here is the probability when x is equal to 3. My P and Q, well, this should be pretty straightforward. The probability of flipping a head is 1/2. The probability of flipping a tails is 1/2. Raised to the exponent, there's 3 fails before you get your success, which gives you an answer of 0.0625. So there's a 6.25% chance that you will get $8 in a single play. Does anyone have any questions? Okay, the next one here. What is the expected number of games you'd need to play in order to get a win? So again, here I have the expected. Oh, I didn't mean to do that. The number of expected wins is equal to, so again, as soon as you see expected, we do our 1/2 divided by 1/2, which is saying 1/2 times 2 over 1, which is equal to 1. So again, you would expect 1 fail before you get a success. So you would expect to flip 2 times. Okay, anyone have any questions about this right now? Okay, the next one is maybe a little bit more abstract. It says here, what is the amount a player would expect to win playing this game? Okay, it doesn't really give us a limit. It's just saying what it is expected. So I have here, my outcome is x equals 2n. And then I'm going to be doing the chart here where the probability of that happening. So if I get in 1 flip, that would be saying the first head, I would get a value of $2 if a head would be there. What is the probability of that happening? Can you help me out, Powell? What's the probability of me flipping a head on the first try? Good. 1/2, which is 0.5. Okay, if I get it on 2 flips, the total value which I will earn is $4. What is the probability, Mitchell, of that happening? Yep, 1/2 times 1/2, because that's the probability of getting a tails times the probability of getting the head, which is what we want on the second flip, which gives us 0.25. Then I can go to 3 flips. How much money would we earn in 3 flips, Spencer? $6. Scott, what's the probability of me getting that? 1/2 times 1/2 times 1/2, which gives me a probability of 0.125. Okay, on my 4th flip, Curtis, how much money could I expect to win? $8. And if I have $8 here, what's the probability of that happening, David? Good. Okay, this is going on further and further and further. What do you notice? Okay, I'll do the next couple for you. For 5 flips, which would be $10, the probability of that happening is 0.0312. The probability for $12 would be 0.0156, and you can continually do this. The probability of $14 would be 0.0078. You're going to notice that these probabilities here are getting smaller and smaller and smaller and smaller. Like you can continue this and you can actually figure out what would the probability of getting $40 be. It's actually 0.000. So when you're doing a question like this, we actually, the probability that it will happen, that the more money you win occurs less and less and less. So we don't need to count every single case for this because these probabilities are really, really small. So in order to get an expected value, we're just going to, again, get a good general feel for this. And then this goes back to what we did last week. What I can do here is the expected value for the win. I would take 2 times 0.5 plus 4 times 0.25 plus $6 times 0.125 plus $8 times 0.625. And then this is going to go on and on and on and on. And those other numbers are going to be very close to 0. So we're really only going to look at these couple of numbers because then we're talking about very, like, not even, a percentage of a penny. So we're looking at these first couple of cases here to get a good idea as what is expected. And you would expect here that if you were to play this game, you would expect to win $3.25 if you do that. So you don't have to do all cases, because we'd be here for a very long time because there's no end limit. But we know that that end limit is very close to 0, that could happen. So we just stop looking at those numbers that are really close to 0 and only look at the first couple to give us an actual reading for this. Okay?